Welcome to your lesson on modeling with similar triangles. I'll be your host, Mrs. Logan, taking you on this incredible journey learning more about similar triangles. For example 1, we're proving that triangle ABC is similar to triangle XYZ. Now we already know that angle B is equal to angle Y because they're both marked as 90-degree angles. However, we need to show some more information to be able to prove that they're actually similar to each other. Now we have all three side lengths in both of those triangles, so we can actually look at their ratios and see, do we have that proportionality? So if I look at the smallest side in triangle ABC, that smallest side is BC, which is 3 centimeters. The smallest side in triangle XYZ is 9 centimeters. So if I compare side length BC to side length XYZ, that ratio would be 3 to 9. Which is equivalent to 1/3 in lowest terms. If I look at the next longest side in triangle ABC, it's 4 centimeters long, and that's side AB. The side that corresponds to that would be side XY. Those measurements are 4 and 12. And when we put that in lowest terms, it's also equal to 1/3. That's a good thing. And then when we look at the hypotenuse of our triangle, we have side AC being divided by side XZ because they correspond to one another, the longest compared to the longest, and side AC is 5 units, side XZ is 15 units. In fact, the units are centimeters, and in lowest terms, that ratio is 1 to 3. So once again, we have proportionality. All three ratios are equal, so since we could write that as BC compared to YZ, that's equivalent to AB compared to XY, and that's equal to AC compared to XZ. So since all sides are proportional to each other, we can conclude that triangle, so therefore triangle ABC, is similar to triangle XYZ. And that's through side-side-side similarity that we talked about yesterday. All right, your turn. Explain why triangle GHI will also be similar to the above triangles. So you already know that triangle ABC is similar to XYZ, so just pick one of the two triangles, maybe ABC, and compare it to triangle GHI and see if your side lengths give you, corresponding side lengths are proportional to each other. I'm going to compare side AB, which is the medium side length, and I'll compare that to the medium side length GH on the triangle that we have here, and that is equivalent to 4 divided by 8, which is 1/2. All right, now let's check the small to the small. Let's go BC compared to my small side in the other triangle would be HI, and BC we know is equivalent to 3, HI is 6, and 3 divided by 6 in lowest terms is also 1/2. And then the last pair of sides would be AC being compared to GI, and that would be 5 compared to 10. And you clearly can see, I mean, you probably could have figured this out, but we're just formalizing it in a proof that these side lengths are proportional to one another. So that means that we have AB over GH. That fraction or ratio is equivalent to BC over HI, and that's equivalent to AC over GI. So then that means that triangle ABC is similar to triangle GHI. Okay, so your turn here. How many times longer are the sides of each triangle compared to triangle ABC? So triangle ABC has the smallest sides of all of the three triangles. So if you compare to GHI, think of the corresponding sides. What are we actually going to do to the 4 centimeters to get to 8 centimeters? What could we do to 5 centimeters to make it equal to 10 centimeters? And the same thing that we could do to 3 centimeters to make it equal to 6 centimeters. Have you got it? Wait for it. Okay, hopefully everybody's had time to think about that. The sides of triangle GHI are 2 times, that's right, 2 times longer than the sides of triangle ABC. Look at triangle XYZ and compare it to triangle ABC. We know the 4 matches up with the 12. How many times greater is that? 5 matches up to the 15. How many times greater? 3 matches up with the 9. How many times greater? Yeah, you're right. That is 3 times longer. So you'll notice that if I flipped all of these over, all of these ratios over, that would just be a 3 to 1. A 1 to 3 or 3 to 1, really it's just the order in which I'm comparing them. Likewise with the other ones, I'm comparing ABC to GHI. The GHI is twice as long as the ABC. The XYZ is 3 times as big or as long in side lengths compared to ABC. So you'll notice that these numbers match down here. All right, your turn. You're going to determine the perimeter of each triangle. Remember, perimeter is just the distance around the outside of the triangle, or the length around the outside. So calculate the distance around the outside of each of the 3 triangles, and then we're going to do a comparison. Also, you're going to calculate the area, and remember, area of a triangle is just base times height, divide by 2. So take a few minutes, put this video on pause, take a few minutes. However, before you do that, I forgot to write this down. These numbers of 2 and 3 here, these are known as, or called, the scale factor or scale ratio. So scale factor, factor just means things that you multiply by. So we're multiplying sides by 2 or sides by 3 to get the new side lengths. So scale factor or scale ratio. Okay, now you're going to calculate perimeters and areas. Put the video on pause and then we'll take it up. Okay, and I've worked my magic here. I've calculated the perimeter for each of the 3 triangles. I've also calculated the area for each of the 3 triangles. So hopefully you have the same answers that I have for your final answers. But we're going to talk about these briefly here. I want to compare the perimeter of triangle ABC. So perimeter of triangle ABC. I'm going to compare that area to, or sorry, that perimeter to triangle GHI's perimeter. So if I look at these 2 values, I've got a 12 and then I'm comparing it to 24. You might notice that that perimeter is doubling to get to the perimeter of GHI. Similarly, if I compare the 12 centimeters to the 36 centimeters, I would actually be tripling 12, multiplying by 3 to get the 36 centimeters. Now those numbers actually correspond with our scale factors. Okay, so the perimeter is directly related to the scale factor. Now I also want to show you something else here. I'm going to write a little step in here. You don't have to copy this down, but you can if you wish. You can write it underneath the 24 centimeters. What I'm going to do with the 6, 8, and 10 is I'm going to do something called common factoring, which we've already talked about to a great extent. Each one could be divided by 2, so I'm going to put a 2 on the outside, and then we're going to have a 3 plus a 4 plus a 5. Now, we don't normally do this, but I'm just showing you the other thing to look at here. Do you see that 3 plus 4 plus 5 is what the original triangle ABC's perimeter was? The 3 plus 4 plus 5. I'm just doubling it. I'm timesing it by 2. Okay, kind of cool. Similarly, I could look at triangle XYZ's perimeter, and all 3 numbers, the 9, the 12, and the 15, are all divisible by 3. We can pull out a 3, and we're again going to get 3 plus 4 plus 5 inside that bracket. And that's pretty cool, because that, again, 3 plus 4 plus 5 is triangle ABC, and you can clearly see that we are multiplying that perimeter by 3 there. All right. The next thing we're looking at is the area down here. Now, if I compare my 6 to my 24, it's not 2 times as great. Instead, if I do 24 divided by 6, I would get 4. It's actually 4 times bigger. That's a little curious. Now let's look at this one. Is this 3 times bigger like it was above? No, sadly it's not. However, if I do 54 divided by 6, I now get 9. It's not 3, it's times by 9. Why is this happening? Why is it not just times by 2? Why is it not just times by 3? Well, let's think about this. Let's talk about the fact that each side length has been doubled. Each side length has been doubled. So the base got doubled. So that 6 really was 2 times the 3, the side length that was 3. And the 8 really was 2 times the side length of 4. So the 6 is 2 times 3 and the 8 is 2 times 4, and then divide by 2. We're doubling 2 dimensions here. We have to times by 4 because we're doubling the base and we're doubling the height. So 2 times 2 is 4. If I look at my XYZ triangle, I'm not doubling my side lengths, I'm tripling the base. So originally the base was 3, now it's 3 times 3 to get the 9. And the side length, that's the height, the 4, it was also tripled. So my originals are the 3 and the 4. This was the 3 and the 4, the 3 and the 4, the 3 and the 4. I'm now 3 times 3. An extra factor of 3, an extra factor of 3. So that times by 9 is really times 3 by 3, or 3 squared. 1 for each dimension. So again, that's pretty cool. All right, from here we're going to look at a couple of problems on the back of this handout, but I'm going to start a new video for that.